Take 7922. Good afternoon and welcome back to my workbench, where today there's no power cut and I'm going to do something with electronics as usual. So, this video is going to be to do with this little preamp circuit, which I have had lying around for the last 20 years or so, after never really using it for what I originally wanted it for, and now I've decided I would like to use it as a way to preamp my cell phone headphone output so I can run it off my standard stereo system without having to turn the volume controls up all the way on both the phone and the stereo, basically. If anyone's ever done that, they'll know that that's kind of an annoying thing you have to do. So I want to have a preamp that avoids that problem and allows me to have the volume levels set normally, and then this will do all the work instead of having to turn everything up. But before I can use that, I need to get a power supply for it. So it needs a split 15 volt rail, positive and negative 15 volts, and I had originally created this little board on some strip board with a couple of voltage regulators for it using this transformer, but it never worked properly. These regulators are 7915, and I wasn't getting 15 volts out of them. I was getting like 18 or 19 volts or something weird. Don't know what was wrong with it, but there's something funny going on. It never worked properly, so I kind of gave up on it. So yeah, I want to redo that, and I also wanted to make this as another sort of part of the homebrew PCB thing, for the purposes of one, testing out the Chinese yellow transfer paper I bought. I've got that over here along with my other stuff. Let's have a look. So that I've just stuck in here. I mean, you've got the you've got the blue stuff, which I bought, Pulsar Pro stuff. That's what I used last time. That works pretty well. And then there's this yellow Chinese stuff I got off eBay for about, I don't know, a lot cheaper anyway, and I want to see if it works. Someone in one of the comments, someone asked if I'd tried it out yet, and I hadn't, so I thought, well, I should probably do that, because I do want to know if it's any good. I've been told that it's alright, but you know, I don't actually know how good it is compared to this one, so I want to find out. Anyway, so it's leading up to an excuse where I get to test this, and I mean, I could just print any old design out and test it out, but I figured that if I was going to go to all the trouble of actually bothering to do that and making a video about it and everything, I might as well use a design that I actually want to make anyway. So I figured that getting this all working and making a board to do the proper voltage thing and everything for this, I'd use that, and that allows me to do that both at the same time, and we get to test this out and get this working, and I also get to make this video, which will be sort of a tutorial on how to create a printed circuit board design from scratch, and also draw up a schematic from scratch and all that. So in comparison to the work I did on this power supply here, where I just basically scanned a pre-existing layout like the one in this manual here, you know, just the board layout like this, I scanned it out of the magazine and printed it out and everything to make the PCB for this supply. Instead I'm going to look at sort of like, what do you do if you don't have that? What happens if all you've got is a schematic, and you know, or whatever, which you could have found in a magazine or online, or you just, you know, or you already had it made up yourself or whatever. Just looking at how to do that, and also making a basic sort of design for these voltage regulators, and looking at some of that. And so kind of I'll be putting together a basic schematic for a split rail power supply, and also yeah, and then showing how to create the schematic for the PCB layout from that. And I'm going to be using KiCad on my computer here, which is my preferred EDA tool, electronic design automation sort of CAD thing for doing schematic capture and PCB layouts. A lot of people I know use Eagle. Well, not people I know, but I know that a lot of people use Eagle, which is actually a program I tried myself. It was the first one I tried. After doing boards by hand, just on graph paper and that, which is how I originally started doing it. But to do it on the computer there, I originally tried Eagle, and I really didn't like it. I just didn't like the way it worked, and I didn't like the limitations of the free version. But KiCad, in comparison, I much prefer the way it works. I much prefer the interface, and I just much prefer the fact that it's completely free and it works on Linux and Mac and Windows and has no artificial limitations. You can have up to, like, I don't know, 16 layer board or something, I think, and size is just infinite. Basically, it's whatever, however big you need it, any shape, all that kind of stuff. So it's much, in my opinion, it's a much better alternative to the free version of Eagle. Eagle's probably okay if you pay for it, then you don't have the layer limitation and the size limitation, but I still don't like the way it works, so I'd never want to use it anyway. KiCad obviously is really good for hobbyists because it's not super advanced. There are things like Altium and OrCAD and software like that is going to have a lot more more features and things that KiCad doesn't have, but they're all the kind of advanced stuff that most hobbyists in that will never use, probably. And yeah, I mean, there are some things lacking in it which I wish it did have that I would like to use, like, say, free angle routing or something like that, but most software doesn't have that anyway. But yeah, relevant to do with what I'm talking about, but yeah, that's just my sort of rationale behind why I use KiCad. So I'm going to be using that whenever I show something to do with board design or whatever on here. It'll always be KiCad because that's just the one I like using. Okay, so we're over at the computer here now, and I'm doing a screen capture for this, and I've just gone to the KiCad website. Current one is kicad-pcb.org. You can download the latest versions here for, like I said, Windows, Mac, Linux, different versions. I'm going to guess that if you're at a point where you're designing your own electronics, you probably already know how to use a computer and how to download stuff, so I'm not going to bother showing any of that, but just to show the website and the options you have. So yeah, everything's there, and if you need help, there's forums and stuff for all the other stuff, and yeah, things like that, documentation, whatever. But I'm going to show basically a basic idea of how to do it. So once you have it installed, just load it up, and you'll first get just a blank screen, nothing on it. So you need to create a project first. So you can click this button here, or you can go File, New Project, whatever. So I'm going to call it Universal PSU. I think the older versions of KiCad had a kind of requirement where you needed to create a folder called whatever you wanted to call your project, and then create a project called the same thing, so the project and the folder name were both the same, no spaces in the path or the folder or the file name. Nowadays I don't think that matters, so you can pretty much call it whatever you want and put it wherever you want, but if you're using an older version, it is worth watching out for that. I'm not entirely sure what happens if you don't do that, if it'll just crash or something will get corrupted, but yeah, I just do it out of habit now. So anyway, something worth noting if you're using an older version for some reason. Maybe if you have an old system you can't upgrade and you have to use an old version, I don't know. Anyway, once you've created your project, you can create files for it. So these are all your different tools for creating, Schematic, for editing footprints, for editing circuit board layout. The first one you obviously need to do is create a schematic. And well, we have to know what we're doing first. So like I said, I'm just going to sort of basically copy the data sheets for these ones. So if we go to this one, like this 7915 data sheet, we've got this little basic example circuit of how to create a positive 15, negative 15 volt split rail power supply. And this is basically what I want for my my preamp, but we want to make it. I'm going to make it a little bit more interesting than this. I want to make it more universal. I want to have it so we can add also a 317 or a 337 adjustable regulators and have the component spaces. If we look, for example, the example circuit for this, where is it? Is there one in here? There we go. So the 317 and the 337, they have a couple of resistors for voltage divider, some other components for stability, and you can have protection diodes and stuff. These resistors are used to set the output voltage because it's an adjustable regulator. So there's no direct ground pin connection, it's through this. So yeah, I'm basically going to have it so we have options for these resistors if you want to use the variable regulator, and if you don't want to use it, if you just want to use a fixed voltage one, then you omit this resistor, omit these diodes, etc. And then you just replace this resistor with a Y link so that that pin is connected directly to ground. So I'm going to make sort of a universal one where you can use either these fixed ones or the adjustable ones, and have all these, like this protection diode is only designed for when the output capacitance is larger than the input capacitance. When you switch off, it might, back drive this thing and short it out, so you want to have this to allow the power to flow through that instead, and yeah, stuff like that which you may or may not need, but I'll put those all in, and so it's just optional whether when you want to populate the board, when you want to build it, you just choose whether you want those parts or not, depending on what you're doing. But the board will support all those different options. That's basically the idea of it. So yeah, so just having a look at this basic design, start with this. So go to this schematic editor, and you want to put the parts in. So quickest way to do that is to click this button here, just place component, and then you just click somewhere on the page, and it'll come up with this window here. So this is your library browser, and the names aren't that great at the moment, but you can download other libraries that have better names. But I stick with this because I don't, I'm used to it anyway. So say that we want like a 7805, we can just search for that, and it'll come up. This basic one here is not very good because it doesn't have pin numbering on it, but we can choose this one here. This has the correct numbering and everything. It's just easier to use, otherwise you have to fix that later in the editor and it's just annoying. So we'll put that there, and we want the opposite, obviously the 7905, and I'm choosing the 5 volt regulator not because that matters, but all of these are the same pin out, they're all the same design, so if it's a 5 volt or a 9 volt or a 12 volt, 15, whatever, it's all just the same. But we're not going to add, there's no generic thing. But this footprint, well, not a footprint, this symbol here doesn't refer to any particular part really, it's just a generic representation. You can assign it to whichever part you want later. So there's no footprint assigned to this at the moment. I mean, it says TO220, but I could assign this to a TO92 footprint if I wanted to. I could assign it to whatever I want later on. So if I wanted to make a version of this board which used like 78L05s, the little TO92 small current ones, I could just associate that with that and change it, and I wouldn't have to change this symbol here. I could just keep it the same. So I find that quite useful with KiCad, and something like Eagle doesn't do that, and I don't really like it. But anyway, because these aren't specific to the 5 volt regulators or anything like that, I'm going to edit these names. You can just hover your mouse cursor over the lettering and press E, and this will bring up this edit field, and I'm just going to change this to say 78XX because I'm just going to say it could be anything, and the same with this 79XX. I'm just going to put that like that, and we also want, if you hover over, press M on your keyboard, that gets you to move mode, and I'm going to add also an LM317 as well. So that's the adjustable version, basically of the same thing, and I'm adding this separately because the pin out is different. For this, you can see the pins are all completely the opposite, basically. So whereas with the 337, which is the negative adjustable one, and I can show you that here, LM337, T version is the TO220 version. If I put this next to this one, we can see that the pin 3 is output, pin 1 is ground adjust, similar, very similar. You just have the resistor to ground. Well, this is connected directly to ground. The input is pin 2, so these are all exactly the same basically. We don't need this. We can just fit that in the same footprint, whether you want to have the fixed or the adjustable one. But with these ones, the pinout's different, so I'm going to have both of these in at once. I'll create 2 footprints that are separate but just right next to each other, and then it's basically, when you want to solder the board together, you'll just choose whichever one you want and put that in, and the associated resistors if necessary, and yeah, so it just makes it easier having one designed board for various options. And like I said, but yeah, these particular ones, the pinout's different, so you can't just drop it in. This one, well, yeah, I mean, this one I can edit this LM79X/LM337 because it's the same pinout. We can just drop those straight in, depending on what we're doing. So I'll move this down a bit. Oh yeah, another thing worth noting is this cursor I'm using. You can turn these lines off if you don't like them. I personally do like them because it helps you line things up. Like I can get this line here and I can see all these regulators are all in line vertically. So yeah, it just helps with that kind of stuff. I like it. But yeah, if we go to this basic layout here, so we want an input capacitor of some kind, an output capacitor. Again, like it depends which regulator you're using. If you're using this one, you might have these values. If you're using the 317, you might have a different value. Yeah, so whatever you're using, I'm just going to put in a basic capacitor for each one. So if I go type in C, just get a capacitor. Could be anything. There's no assignment with value or type or size or anything, physical dimensions at this point. We just want a basic thing, and you can put another one in on the output. We also need some down here. Now these ones show non-polarized and polarized. I don't really know why. Probably because these are higher values, so it would make more sense. That's worth taking into consideration. So I'll put in a type CP for polarized capacitor. Again, this is kind of KiCad, being KiCad, that the default libraries are called this. That's what they've been called for years. So the fastest way to get what you want is just to type that. We also need these diodes. So again, go to parts, press D. The first one comes with a diode. This is for all your basic components, diodes, resistors, capacitors. It's easy just to type the first letter of the device and it'll just come straight up. Also worth noting, if you want to rotate your parts, press R on your keyboard and it'll rotate them. You can rotate them afterwards obviously, but while you're putting them in you can do that too. So we want to have this here, another one down here, and that's pretty much it for the basic design. So then you have to hook everything up. So you go to the wire mode, which is this one here, click on that, and then you click on the pin you want to connect once, go over to what you want to connect it to, click once again. The older versions of KiCad you had to double click, so the new ones it's just one, so that might be worth noting if you are using an older version. If you wish to connect these two though, you will have to double click, I believe. So let me just test that. One click. Oh no, that works, but in some cases if you say connected this around to here, I think, oh no, it works. Okay, that's interesting. Right, so anyway, connect these all up, and now it's starting to look sensible. This obviously, I'm going to move this down a bit, so hover your mouse over the part, press M, you can move it down. I'm going to click create a power connection here, so we can just type ground. This makes the schematic look neater, so I can put a ground symbol there, and I can put one. Oh no, actually I don't need to put one here. I'll put this as the actual rail going straight through. So that'll go straight through as a ground. There we go, that can go like this. And then if we have coming out here, we can have the ground symbol. So this is our ground net here, and then this pin is going to be connected to the same connection because it's got the same ground label. So this also goes up to ground there. Now this would connect directly to ground if it was a 7.9 series regulator. If it's a 337, it's going to have a resistor. So I'm actually going to go back here, press R, resistor, and I'm going to put this here, and I'm going to put a note next to it to say R for 337 slash wire link for 79XX. I'm going to create that text a little bit smaller. For example, we can put that there, so that's a good note. You know, it's telling you that this is going to be what it is. So a good schematic will have notes like this, especially if there are different options for components. So what it's saying is that if this is an LM337, we have a resistor going from that pin to ground. If it's not, if it's a 79XX version, then that's going to be replaced with a wire link. So we just want it to know, so that anyone reading this will know what that's doing. So yeah, good idea to put notes like that in your schematic. And if we connect this up there, and this will connect up there, this will connect down here, and we need to do the same basic thing with this. Now I've run out of room, I guess, here. I can't really put another resistor in. If I put this here, it's going to be too close to this, and I can't sort of... Well, I could, but it's not going to look very good. So I want to move this down a bit. So let's just put this resistor over here for 1 second. And what I'm going to do is click and drag and highlight these parts here. And then I can right click and go drag block. And that means I can drag these down and I can actually extend the wires. So I'll bring that to about here. And it'll automatically extend the wires. If I did that without going drag, it would just move everything like this, which is not ideal. So I just want to move this over here. We can connect that like this, and then this can go to ground here. This particular one, there, out, it's going to go there. And if we check the datasheet again, the basic idea, we have a resistor going from output to adjust, and then we have a diode here and a capacitor here, for whatever reason that's for, the datasheet will say. So we want another resistor, so it'll go there, and then again we have the same problem where there's not enough room to put the next parts, so we have to move these over. So grab this again, and either right click and choose drag or press tab, and then that'll extend these out. So we've got more room, and actually this hasn't, I don't know if that's connected, so I'm going to delete that wire. You just hover over it, press delete, and it'll come up with this. So it's asking me, do I want to delete this part here, or do I want to delete the wire? I just click on the wire. So I'm going to move this down a little bit. If you don't have one of these junction dots, it may not be connected, so just to yeah, just to be sure of that. Actually, so we've got this here, and the same goes for this side. We need a resistor, so if I want to copy this resistor, for example, I can just put my mouse over it, press the C key, I choose I want to use the component, and it'll copy it here. So for the output, we want that, and that will go to this side. So again, we have the same problem. I have to move these around. So yeah, good good point to make for that. So I can move this. If I press G over it, drags the whole thing because these two are now connected together. So that's not very useful. If I move this back and then I can create a thing here. Actually, move this around. There's a lot of moving stuff around this kind of thing. Move this. But yeah, that's starting to look alright. This we can line up with this, but that's done a silly thing. So let's just delete this wire, delete that junction, do that again. So there we go, things are starting to look sensible. What else do we want? Oh yes, a diode in parallel with that resistor and then a capacitor. So, a diode, it's going to go here, and we want to have the same thing over there. I'm pretty sure, and then a capacitor to the ground. So yeah, we can have a look at this. I mean, what does it say here? Protection diode D2 is recommended if C adjuster is used. This diode provides a low impedance path, protection that with the regulator. And C adjuster is recommended to improve ripple rejection. So yeah, so I mean, if you're using this, it's a good idea to use that, and if you are, you should use a diode. So yeah, pretty simple thing. So it's a good idea to have all that there. I mean, you know, it depends on the design, what you're doing, but in general, you probably want to have those there if you're using the adjustable parts. So yeah, so that gives us that, and now I've got pretty much everything we basically need. I'm going to add an option for some big filter capacitors over here. Because you know, you may want these on board, or you might be driving this directly off a transformer like I will be, or you may already have filter capacitors somewhere else and so you won't need them on here. You'll just need the decoupling capacitors basically. So yes, that'll be like optional thing that you may or may not want. Again, it's all basic in the design. And what else? We've got our output decoupling, input decoupling, main filter capacitors. We've got all our adjustment things, protection parts for the adjustable regulators if we're using those. Again, if we're not, you just take all those parts out. Let's put the reverse protection diode across the back of the regulator. Again, this only is necessary if your output capacitance is higher than your input capacitance, i.e. if the bulk filtering capacitor here is lower than the whatever it's driving. But in general, you know, you don't necessarily need that every time. And obviously the one here, we want to have it in the other direction. But yeah, so there we go. That's a basic sort of regulator thing. We could also add maybe a potentiometer trim pot in series with this resistor or in place of it as another option. I might do that later depending on how it's going to look on the board, but yeah, probably not really what most people would use, but yeah, I mean, if you want to trim it to be accurate, I suppose, yeah, we could put that in. Just thinking, how could you do that? Whoops, that wire's not connected. See, that's that little square there, it means it's not connected. So let's delete that. Whoops, no, let's delete that wire and reattach it. And we see it's actually had been connected to that part instead of the junction. So good to watch out for things like that. Sometimes that happens, sometimes they don't connect where you expect them to. So if things don't make sense when you start laying out your board and stuff isn't connected where it should be, check that. Now that was hang on, that diode's completely in parallel. Yeah, that needs to be connected here too. See, I'm already making silly mistakes. It's kind of late in the day, but yeah. Anyway, good idea to watch for that sort of stuff, because if you're a beginner, if you haven't done this before, it's really easy to make silly mistakes like that and mess things up. So good idea, once you've done something like this, finish it off, come back the next day, look over it again, and just make sure that it makes sense. I'm going to move that text over here so it's not being cut off by that wire. So yeah, that's what else? Okay, so I want to have this for my transformer, so we're going to need some sort of rectifying diodes over here. So I'm going to go with diode. I'm going to go with, option 4, discrete diodes, and I'm going to need to put a connector, I think. So we're going to put connector, 3-pin connector, because yeah, that's what we'll have if we have a center tap transformer. That would go, there'd be a center tap would go to ground, and then you'd have your diodes going here. So one side would go to one of these diodes, that would be a positive. We would have another diode there, and that would go down to this side. So whichever one of these is positive, it's doing full wave rectification, and you can see that that hasn't been connected either. So I'm going to delete that wire. Whoops. Yeah, so this is where you need to double click. Sometimes you need to double click and sometimes you don't. It all depends on what the thing's doing, which can be kind of annoying. Anyway, yeah. And then we want our negative rectification diodes for the negative rail. So let's put that in. So this would be your typical way of doing it. You'd have your full wave rectification, and then this would go over to this pin, and this would go to this one. Now we can see these wires overlap, but these ones aren't connected because they've got no junction there, neither are these ones. So it's all about whether or not there's a junction or not. So yeah, if we had a center tap transformer, full wave rectifier for both sides, that's how it would look with 4 diodes. I'm going to do discrete diodes here instead of bridge rectifier, because there are so many different versions and shapes of bridge rectifier, different sizes, that trying to accommodate all of those would just be really annoying. So I'm just going to go with discrete diodes, and that also gives you the option to change that as well. So for example, if I wanted to have, if this was, depends on what current level, this thing I'm going to be making is going to be like I said, 10 milliamps or something, so we can use whatever diodes. If you had a higher current thing, you'd want to have maybe bigger diodes than the 1N404, whatever I'll be using. But of course these things can only go up to about 1.5 amps anyway. So, but yeah, that would make sense for that. If we wanted to do half-wave rectification, like I'm going to be doing with a non-center tap transformer, the option for doing that will be a bit different. So I'm going to move this over here a little bit, and then if I was doing that without, oh, let me think. So if I have that half-wave rectification means that one of these pins, there will be no center tap. One side of the winding will be directly connected to ground, so that's okay. We can just say we just leave that open. I wouldn't connect anything to it, and if I was to connect these diodes, I'd have to let's put another set of diodes. Or would we? Hang on, we'd still use one of these. That would work. Actually, yeah, no, what am I talking about? Basically, yeah, for full wave rectification it'll be like this. For half wave, you would omit these ones. So I'm just going to put a little box around these. Put another note here. I'm just going to say so yeah, oh actually, and pins, well, let's say 2 and 3. So yeah, so basically, if you're going to use a center tapped transformer and you want full wave rectification, you put all 4 diodes in. If you just want half wave, you omit these 2, and then you just connect your transformer to these 2 pins here, which means that the this diode will be doing the negative rectification on this side from this pin, and this one will be doing the positive on this side for the same pin, and then this will be your other side, which will go to ground. So what that means is that these capacitors will only get charged up half as much as they would, well, not half as much with power, but half often, because they're doing it on each half cycle of the sine wave, which also means that your input voltage will need to be a bit higher than it normally would be, so that the ripple, if you want to make sure there's not too much ripple, you're going to want to have the input voltage a bit higher. But you know, I'm doing 24 volts AC rectified. That's going to be even higher, and then you know we're taking it down to only 15, so there'll definitely be far more headroom than necessary to do all that correctly. But yeah, I mean that's basically it. That's basically done. That's the schematic. I suppose you could put a fuse in line with this at some point. Maybe I'd add that as well. Add adjustable trim pot, maybe. You could also put like a power LED or something across the rails if you wanted to do that. But the basic design here is done. I mean that's pretty much what we want. That's pretty much it. And then and so I'll stop the video here, and I'll make the next segment will be assigning all the component values, the footprints and all that stuff, and then doing the board will be in the 3rd segment. So yeah, that took a bit longer than I expected, but that's the basic way to do it. So yeah, I mean that's how you use KiCad to make a schematic. There's also a bunch of other options in that. You know, you can create a bus and stuff. If you're doing a whole bunch of data lines or something, you can connect them all together with a bus, and basically as long as everything's labelled with the same name. If you want to label a wire, you just place this one. So if we had like this, we'd have like, say, input rail positive or something, you know, then everything here is called that. And if I have another wire somewhere, it's the same as like these ground flags, these labels here, you know, anything else I call label with this name will be connected logically to each other. Even if it's not drawn connected with a wire, it'll be connected in the netlist, in the data behind the scenes. So I can, you know, do whatever like that. Anyway, but that's the basic thing. So there we go. So that's the design I want, and I'll get on to doing the board next. Okay, so I'm back for part 2 of this circuit board design video. This part will be sort of labeling everything and associating footprints and all that. And then in the third part, I'll get on to actually laying out the board and doing all that stuff. So this is the basic schematic from what was last time. Obviously I haven't changed anything yet. The basic design is fine, but there are a couple of things I want to change. Just want to tidy up a bit and make some other stuff a bit obvious. So especially with this input here, it's a bit confusing. I'm going to change it round. I'm going to rotate this. We can flip this on this axis, and I'm going to give it a more obvious name. This is going to be transformer. And I'm going to edit this because this is kind of a bit ambiguous. So I'm just going to change this to say 1 and 2. I mean, it doesn't matter. It could be 2 and 3 or 1 and 2, but yeah, yeah. And I'm going to change this note. It's a bit sort of to make that a bit more readable. So I'll put a little box around that as well. So that it's more obvious, and I might move this over a bit, and then I'm going to put a little line just like that, so we get a better idea. Maybe put this here. Yeah. Move this reference over here, move this up a bit. Or maybe put this down. Yeah, that's better. Anyway, so that's a bit more clear. I can delete this label because that doesn't really make any sense. I also need to put a let's rotate this around a bit. And we want to give it an output connector as well, because this is obviously not going to not going to work. So copy that, and I'll rotate that. Put it over here, edit this name so it's output. Bring it over here. Because without a connector or some sort of component to show for this, we don't get any chance of actually putting any pads, because this will be associated with a footprint, so it can have some pads there, otherwise there'll be nothing to connect the output wires to on the board. We just have the diodes and then it will just stop there, so you actually do have to have some kind of thing. Now this ground flag here doesn't look particularly good, it's sort of a bit, yeah, it could be done better I suppose, but oh well, it functions anyway, so I don't mind. Yeah, so for a start, just go around labeling things basically and put your notes in so that if things make sense, then for example this one I'm going to change to 1N400X, just, you know, that's most likely what someone would be using. We could have a higher current one like 3 amp, but not really any point because these regulators aren't going to be running, you know, they're only going to have like an amp maximum, and that current they're going to be very hot, so you're probably going to want to have something else if you're going to do that. This is probably going to be like for designs that are, you know, 500 milliamps or less or something. It's not going to be a super high powered thing. If you want a really high power supply, then you should probably use something else anyway. But yeah, so I can edit these as well. You can sit here and do them all by hand like this, or you should be able to go find and replace, and if I say you know, search for D, so all diodes replace with 1N40X, and if we choose yeah, match case, search ref is no. I think that should do everything. Match whole word, otherwise it'll, you know, change the D in this ground to that. We just want to have it so that only these diodes is labeled as D, and this should yeah, so it's finding this, and I replace all. It should do that, so that that'll work. If I had that set not to match whole word, it would have changed the D in this ground label to also say 1N40X, and that wouldn't be very useful, so you have to watch that. The bit where it has this question mark, that's the reference designator, so that would be like, you know, C1, C2, C3, C4, etc. You don't really need to do those manually unless you really want it to be manual, but there is an automatic annotation feature that'll do that for you, so you don't actually have to bother. Yeah, so I suppose I should put a thing around this as well. Let's see. Let's put a little box around all these parts. And a note that says optional 3 7, yeah. And I mean, this might seem a waste of time. you know, to put all these notes, but it is quite sort of important, really. Especially when you go back to the design later on and you wonder why you put such a thing there. It's really useful. It's like comments when you're writing code and that. It just really helps, and especially if you put the design out on the internet or something for other people to look at. It just it really does help for other people having a look. So yeah, I mean, I think that's pretty much good enough. I'll change. Let's see. So these will be the input filter caps. Again, those are optional, unless you know if you want the filtering on board. If not, I mean, I'm going to call these. Let's just say like 2,200. I'm not going to bother putting a voltage on them because you know who. Could be whatever voltage you want. I mean, if you're going to make a 15 volt supply like I am, then these are probably going to be, 25, 35 volt parts. If you're making a 5 volt supply, then 16 volt parts. So it's all going to depend on what anyone's doing. I'm just going to, leave this here, large value, so people know there's a filter cap. This will be, again though, yeah, I don't know. Is there any point for this? I should just label this more, I suppose. Let's go back to the, hang on. Let's go back to this here. So, typically this resistor is always going to be 240 ohms, I think. You need to have at least a 10 milliamp load or 20 milliamp load on these type of regulators, otherwise they won't regulate properly. So something there, 120. Okay, they say 120. This is 240. I don't know, that should probably be... Yeah, let's change that to 120. And of course these particular ones, I'm going to call it R adjust, because that's always going to depend on what voltage you want out of them. But these will probably be 120 for most people. Okay, what was that? They called it C adjust. I'll just call it that, because the value again is going to depend on what you're doing. So yeah, probably that's about good enough for now. I'll change the values later, maybe, if there's anything specific, but that's pretty much it for what you'd want. I'd put a note, in here somewhere later on about what values when I have a bit more of a look at that. See if any of these have any generic values that would be the same value for all the time, no matter what you're doing. I think but really it's going to depend on the circuit itself. So yeah, that'll be good enough to start with anyway. So once you've done that, you need to create your netlist. This actually tells the rest of the programs what's connected to what. So you press this button here, generate netlist. Just use default if you're using everything in KiCad. I've never actually used any of these other options, so yeah, just use that one. If you want to use KiCad's own PCB editor, so click generate, and it'll want to save this netlist. Just use the default name, unless you want to be confused. So now, of course, it'll say, well, I haven't annotated anything. There's no reference designators for any of these parts. They're all just question marks. So it will tell you that you can do this manually yourself with the annotate button, but this will let you, it'll just do it automatically when you want to create the net list, which is quite useful. So you just tell it to do the entire thing just automatically. The default thing is just fine for most people. And again, if you want to manually pick anything specific, you can do that, but that's done that, it's labelled everything, and that'll make sense. So now the next part is to go to this program, CvPcb. So this will this is the part where you associate each of these symbols, schematic symbols, with the actual physical part. So let's see, some of these associated footprints, legal entries. Okay, let's try that and see what it does. Okay, so it's picked up that these are TO220, that's useful. So yeah, so this will now have a big list of all your parts. And we do see here that, for example, this one's still called just C, and this is just capacitor polarized, and it's kind of a bit, not that useful, so it is better to give things decent names, but that's okay. Like I said, it doesn't matter at this point, but there we go. I mean, for example, take these two capacitors here, C1 and C2. We know these are our main filter capacitors, so they're going to be quite large. So we want to choose, now you have this list here of all the different types of components. You can either filter by library, you can filter by pin count, or you can filter by keywords. Now I personally use like filtering by library because it just makes more sense. So obviously I'll go capacitors through hole, that's what I want for these, and we can go to like capacitor radial, diameter 16 millimeters, that's probably about right. It's probably the biggest I'd expect anyone to want to use for something like that. The biggest I would probably be using. Length 25, I don't know. Length 30. I think we got a diameter 16, length 30 millimeters, pin spacing 7.5. It actually tells you here, yeah, down the bottom. Although I don't think you can see this down the bottom because it's cut off by the video. But yeah, I mean, I'm going to choose this one here. And if we want to look what it looks like, you can click this button up the top, view selected footprint, and that will show you the basic thing as it would look in the PCB editor. And if you press this button here, it'll give you a 3D version. Not all of them have 3D things, but you can have a look. You can have a basic look. It's a capacitor. It's what you'd expect, a basic sort of 3D model. So I'm going to start with that for a start, because I'd say that would probably be the right ones. You just highlight the thing you want and double click. I mean, for example, all these ones, all the diodes are all exactly the same, so we just go to like diodes and choose DO41. I think that's the correct one. Yeah, that makes sense. So we could have it like that, or we could have them sitting vertically. Well, that doesn't have a 3D thing, but if you want to do that, I'll just go with this horizontal one to start with. But I might change some to a vertical one if I need the space. I can always change it later. Now these ones here, transformer input and output, I'm just going to go with connector. Just choose, wait, no, that's not in there. We want, let's see, if it's just a basic connector, oh yeah, I usually just choose a pin header. This is a bit kind of crusty to do it this way, but pin header, let's see, straight 1x3, because each one's 3 pins, and we can edit that later. It just gives us 3 pads to work with. We can move them around and change the size afterwards. It doesn't have to be, it doesn't have to be this small pin header like that, or whatever. It's the default footprint, but we can change that to something else. We can edit the pads and everything in the PCB editor later on, so it's fine. There's resistors. I'm just going to go with standard resistor. Resistors through hole. I'm doing this all through hole because I know that's the easiest. Well, it's arguably easier to solder anyway and all that, and that's what I typically go with. But yeah, Let's just resistor 10mm, I think. Let's see. So yeah, I don't know if that's giving a pin pitch of 10mm or a body length. But I'll go with 10 at the moment. That should be, good enough. And these capacitors here, these are all going to be probably really small little electrolytics or film capacitors or ceramics or whatever. So I'll just go, let's see, so I'll just go back to here actually. So we've got C3, okay, so C5 and C6, I think, C adjust, what does it say? So they don't tell you specifically what it is. That's going to depend, probably tell you somewhere else in the datasheet somewhere where it gives you an idea of what that should be, but it might depend on the rest of the circuit. But here we go, okay, so 0.1 microfarad input, 1 microfarad output, pretty small. Blah de blah. So yeah, I'll just let's see. I'll put them as I think these are small. What's this rectangle? Oh no, that's quite large. Let's try that one instead. That's your standard sort of sized capacitor, 5mm. No, actually I might go with a smaller pin spacing. Yeah, maybe that one. Disc. Oh, that'll do. Is that a disc? Yeah, a small little thing. That's a good idea. That gives a better idea of the kind of thing we're looking at. So I'll make those, all those, and these ones can be just a radial electrolytic or something. So that's probably what they'll be. And the 2.5mm pin spacing will fit pretty much all small capacitors like that, or tantalums, or whatever. So yeah, what did I choose? Radial D3. Yeah, let's just choose that. So that should that'll probably be perfectly fine for everything. So we save this. Yeah, save edit. So this resaves all these footprint names into the netlist, so that the PCB editor knows what to load when you load up the netlist in that. And then you can just close out of this, and you can go back to the schematic. Now, I have noticed with the older versions of KiCad, that was all it was sufficient to make the netlist work, but for some reason in this version 4, probably a bug I guess, you do have to go back here and just regenerate the netlist and resave it, otherwise the PCB editor seems to choke on it and it doesn't work for some reason. So yeah, but that should be basic thing pretty much done. And like any design, I mean, you start laying out the board, you might find that some components are the wrong size, or you need to change things, so it's not going to be all exact, and I'll probably end up going back over this and adding some common values and editing some things maybe, and changing the dimensions of stuff. But for now, I'm just going to leave it as it is. It's all going to be good enough to start with. So I can close this down, save and exit, and should be able to go on to the next bit, which is to load up the PCB editor and actually start making the board layout, which is a nice bit of fun in its own right. Alright, so this will be part 3 of the circuit board design, and this is where we actually start laying out the circuit board itself. So now that we've got the schematic all done, or at least mostly done, like I said, there's some of these components I haven't labelled yet, but I'll probably do that at the end. We've created the net list, we've associated all the footprints for what we want, and now it's just the sorry, what was I saying? Now it's just the task of opening the PCB editor. Pcbnew is what they call it, and now we can import the netlist with this button here. So this is read netlist. You hit that, and you, if you choose just this read current netlist, it'll automatically read the netlist with the same name as the project. But of course, you can browse for a different one if you want. But yeah, you just do that, read current netlist, and everything should come up green, so that's all good. No errors. Typically, if everything comes up red and nothing works, it's probably because you, like I said, you didn't resave the netlist after associating the footprint files, which seems to be the main problem I've had with that, is occasionally it does that in this version 4. But apart from that, anyway, so now it'll load everything up, and it'll just dump it all on top of each other in a big pile there, which is not particularly useful. And you can manually move everything just with the M key again and get everything out, but it's also easier to just automatically get it to just sort of automatically spread them all out for you. So what you need to do with that is create your board outline first. So I want let's see, I want my board, this particular one will be 45 by 73 millimeters. So I'm just going to add a line here, and we choose the layer we want to draw on. I'm going to choose edge, and I'm just going to zoom in to this, where's the origin of the grid origin? I believe it's this top left corner, yeah. Just makes it easier to look at. And I'm going to choose grid, and I'm going to set it to 1 millimeter. I'll just go right up to wherever that's at 0, 0, as it shows down there at the bottom on the toolbar here. And I'll just start there. So we want it 45 down. I just find this is the easiest way to do it. 45 by 73. And I'm just going to turn that back on because that would have been useful anyway. So that's what my board is going to look like. That's the size it's going to be. And then obviously I can just highlight this and move it over to the center of the drawing. So now that's good. So now you can press escape to get out of the tool. Oh, yeah, I should have mentioned that earlier on. You just press the escape key on your keyboard to get out of any of these tools that you're working with. So I'm going to go back down to copper. Actually, we'll choose the back copper because it's a single-sided board. Click this button here. Just manual and automatic. Okay, that should be, the description could be a bit more obvious, I suppose, but oh well. So select that button, right click, and then go global spread in place. And if you go spread out all footprints, you have to have a board outline drawn up first to do this, but it'll just do that automatically. And let's put them all over here for some random reason, but there we go. Right, so that's automatically done that. So now we can start placing them much more easily. So I'm just going to move this transformer one that can go on the side here somewhere, obviously, and then we're going to have our filter capacitors. Those will come in. Well, we can have these. This one's going to be quite tight because yeah, this board is probably a bit smaller than I would have liked, but for what I'm doing to fit in, I have to make it this small. Yeah, so for a start, I should start explaining things. You have all these little white wires, they're called the rat's nest. They're all the unrouted tracks. They show you what connects to what, basically. You can turn that on and off with this option over here. But generally you want that on so you can actually see what's unconnected, what's not connected, all that kind of thing. So basically you sort of start off by putting, line everything up so that the rat's nests make sense. So we should have... Oh wait, of course we need the rectifier diodes first, that's why it doesn't make any sense. Okay, let's bring this over here. We need the rectifier diodes. So if we follow this trace, that goes down to here. This is our first one. And what's the next one? Maybe one of these. I mean D1, D2. It was D1 to 4, so 3 and 4. So first of all, let's put that. To rotate some of these, I'm going to put that there. Hang on, let's see. That's C1, C2. Let's go back to the schematic. So D1 and 3. Okay, C1. Yeah. So that actually should be. That should go here, and that should go there. And then D2, that's one of our negative rail rectifiers. D1, it's our first one. That could go on the edge of the board right here, actually. And D3 is the same. Now, of course, I could stick this straight up here, but then these connections have to be routed across to this side, and if I put this one here, it's much the same thing, because remember these cross over each other. So what we use is we can route the tracks between the pins, which makes things a lot easier. So I'll show that in a second. But yeah, so design rules, track width. So one thing I've noticed a lot of people often do is they just set this stuff up and they start drawing tracks with the first thing they get, and you get a really thin trace if you do that, and they might connect those and then like this, and then that's it, And if we load up the 3D viewer, we can see, these tracks have connected, but they're very, very thin. They're very, that's very bad. We want this to be a power supply. We don't want tiny little wires like that. This is the kind of thing you want when you're doing digital stuff, microcontrollers and just like digital data lines and that kind of stuff. It's not really what you want for a power supply. So that's terrible. So don't use the default trace width, which is really tiny. It's what, 1/4 of a millimeter. So delete all those. That's no good at all. What you need is something a bit thicker than that. So for design rules, this is how I do it. You can set different. You can choose different nets and stuff and add different custom sizes for that. But I personally just go to global design and I just add a bunch of basic sizes. So I go, 0.3. And 0.4, 0.5, 0.8, 1, 1.5, 2. That's usually what I choose as the custom sort of track widths. And you can edit some extra stuff here, add vias, but of course if there's a single layer boards, there are no vias, won't matter. But there we go, and then we can go up here to track, choose something, but I would probably go even 1.5 millimeters for these, because it's big stuff. We want something nice and thick. 2 would probably be a bit Well, I mean, even you could use 2, I guess. It doesn't really matter. The other thing also is the clearance. So check that as well. So where's that? Clearance default, yeah, so change our clearance to, I'm going to say maybe 0.5 millimeters. But if you're laying out, like, you know, if you're doing this as like a first board and that, you might even want to choose like a 1 millimeter clearance. It just makes things easier. And if you you can see these sort of outlines around these pads that will show you the clearance. So this is 1 millimeter between here and here, so that's 2 millimeters between those two. So you could have this up to that close, and you've got a 1 millimeter clearance between these pads, and that's, you know, really fine. If we have a look at a 3D view, you know, that's perfectly acceptable for standard stuff. If you're doing this as a first thing, I guess I would say to probably keep it at 0.5 at minimum. But you know, as you go along and you get better at making these things, at least if you're doing this by hand anyway. If you're sending it to a board house, then you just got to go with whatever their minimum is, and it doesn't really matter. But if you're doing the PCB yourself at home, then, you know, start with maybe 1 or 0.5 millimeters. It just makes it easier, because you might get errors in the transfer and that, and have to touch it up with a pen, and it's easier if you don't have to worry about the the size of things. Anyway, so if I was to do this, I'm going to go with 1.5. I mean, these pads now are too close together, so actually I'm going to move these. So if you right click on a pad, you can go, let's see, hang on, maybe to turn that off. Yeah, okay. Footprint. So you get your cursor there, pad 1, drag pad. I'm just going to drag this out 1 grid line, and that one, well, 2 actually. That gives us a nice big clearance between these ones, because we want to have this. These are probably going to be quite thick wires, so to have enough space for the insulation to come in and all that, it makes more sense. So this will be our ground. That'll just go straight through to these, for example. But the actual outputs from the diodes, well, for example, you know, this diode here, that connects to this pad. That's fine, that's not in the way of anything. This connects straight to this. That's fine, that's not in the way of anything. So we could have this diode over here, right on the edge of the board there. That'll be okay. But this one, for example, while it connects up here, this pad also connects down to this other, whoops, that pad. In fact, if we highlight the thing itself, we can just highlight net. We can click on this here. It shows us what's all connected. So these three are connected to this, and of course, well, this ground trace is in the way now. So it's much better if we just take this diode and move it down a bit to the point that its pad is on the other side, for example. And then it's just a simple case of routing that to there. Okay, what's its problem here? 2 track-ins too close. I don't know. Oh, because we've got a little bit of track there. Let's delete that. Okay. That goes to here. And then these ones go straight out to that, for example. Although it would probably make more sense to yeah, anyway, let's just say that, for example. This is not that great, but let's just have a look. This will go there. So same goes for this one. This one needs to connect to that, so we could bring this to this side. Stick it there possibly. Route that track there. Underneath. This one goes like this. Can move this diode to the side. And that could go like that. So it's just a simple thing of routing bits and pieces underneath each other. There's probably a more elegant way to do that, but hey, it works, and we can sort of well, actually this could probably go up a little bit. Probably move this up a little. Fit that in the middle there maybe. Maybe even bring this one down. Yeah, that would work. Now these are kind of centered on this ground trace here. And then we can, drag these over. So if I look at the 3D viewer now, you can see there's a lot of space there. We can move these over. We could sort of sneak these capacitors into the side here where these diodes are. And that should work. Now, yeah, it's not too bad. I can do this. But anyway, what I do want to note importantly though is that if you start dragging stuff around, if I hover over a component and press G, I can drag it about, and the tracks will follow it. If I press M to move it, it'll just move without the tracks. But the point is that once you start doing that for a bit, if I grab this one, move this over here, eventually we end up with this thing where the traces are all just sort of flying around at odd angles, and debatable whether or not that looks any good. But the point is it's not typically that efficient, so I would say you kind of want to avoid that. I personally don't like doing that, so it's better to delete all the traces like that and just redo them, or just not to move them like that in the first place. So better not to actually drag traces. Better to do them this way. So, oh yes, it also one other thing to note is when you're moving traces about, when you're routing traces, you can press the / key on your keyboard to adjust the corner angle, right-handed or left-handed sort of thing. So depending on how you're wanting to do the auto cornering. Yeah, so anyway, so I'm going to move these down here. Fit them in about this fit, I guess. And bearing in mind here that this this keep out area of the pad is not where the actual component will be. The component body is over here. The lead is going to come down here. There's still going to be like a millimeter clearance between that, so we can cram these in like this. I'm going to have to because everything's so sort of crammy. But yeah, I mean, ultimately I can do that. Of course, something like this, it's not a huge deal how you do it. This is all low frequency stuff, 50 Hertz transformer. It's not going to be a massive problem if you have a bad routing on this. It's you know, it's not usually important, but it is good to try to get these things as neat and direct as possible. So there we go, and that starts to shape up a little bit better. So now things are nicely sort of compact over here. I mean, yeah, we could probably, you know, these capacitors are rather large, and we probably don't need to have them that big. If we had smaller ones, we could fit them in right in there, I guess. But to constrain them to the actual board size, which is what I have to do, so you don't really want to have components hanging off the side of the board, and I wouldn't have enough room for my thing anyway. But you know, we could put this down to like a 12mm one that easily fit in here, which would probably make more sense. I'm just trying to, you know, save as much space as possible. There we go. So yeah, it's we got our filter capacitors, got our rectifier diodes. That should be perfectly acceptable. Let me just take our regulator. Let's just grab this one here. This is our negative rail regulator. Put this, I guess, on the edge of the board because heat sinking. I mean, for the thing I want to do specifically, I don't actually need really any heat sinking. Like I said, it's only like 10-20 milliamp current, so these things will barely get warm. But yeah, it's something you want to look at, depending on what you're doing. So actually, probably would make sense to move this over a bit. Let's have this like in the middle between this, so there's enough room to sort of put some kind of heatsink. I guess depending on how you want to do that. I mean, you could have a heatsink that sort of comes around this way and one that goes around that way if you wanted to have them facing each other, or you could have them coming off the back of the board and that. But for my purpose, that's not going to be enough space to do it that way. Anyway, so I'm going to highlight this net here and use it to find out which components are still connected to connect to this. So we can have a look at here. We can see it connects to our output connector at some point, but that will be, yeah, let's stick that in the let's put that like here. That makes sense. Have this on the edge there. So what's our input to this actually? Input to this is the center pin. Okay, so that makes things a little bit trickier. So that's our output pin, and this is, well, not our ground, but our adjustment pin. Ground if it's a fixed voltage regulator, and adjustment pin if it's the adjustable one. So yeah, let's have a look at the input pin first, which is this pin here. So we could just say let's just route this, just right now let's just route this like this. Of course, this is this doesn't like it because my clearance is too big. It overlaps to these pads, but of course that's not a big deal. So we can turn the DRC off. This has online DRC, which means it'll prevent you from connecting something that doesn't make sense, prevent you from making errors, which is quite useful. You can see when that's turned off, you get this little question mark thing. It tells you that you can do stupid stuff like, you know, I can draw this straight over the top of this other track, and it'll let me do it even though that's shorted that track to that one now. If I turn DRC back on, then it won't let me do that. It'll just, if I double click to place the track down, it'll just cancel out of it. So sometimes, for example, like this particular thing here, where the clearance for these pads violates the global clearance, then it doesn't matter, I can turn that off and it's fine. But for other things, sometimes you want to make sure you don't leave it off the whole time and do something that doesn't make sense. So yeah, anyway, that's obviously not the best way to route that. It would make sense to probably move this actually up here. Bring this along there. Again, turn DRC check off. You can back up on the previous segment by pressing the backspace key. And then, yeah, I'm just going to put that there. So that makes more sense. And then we can say, where's our input decoupling capacitor, for example, which we don't really need because we've got the filter capacitors right there. But say you didn't have those, you were running from a already rectified and filtered thing. Click on this, get our input. So that's what's that? That's this one here. So we want to bring that around maybe to, maybe we could stick this there. We don't want to stick it too close to the regulator, obviously, because we don't want it to overheat. But at the same time, we also don't want it to be too far away, otherwise it defeats the purpose. So, it's a good point. If your regulator is going to be running pretty hot, or stuff like that. Also, for example, decoupling capacitor, we want that sort of inline. So if I put this up here, for example, and then I ran a trace to that, the current flow is just going to kind of go past that. It's not really going to do what you want. It's kind of a bit pointless. So basic sort of logical things here. We don't want that. We want this to be basically directly in the path. So if we have this here, we want to probably delete these segments. Bring this so it's more like there, and then it has to basically the current has to flow to that pin of the capacitor before it gets to the IC, so there's no way for it to sort of bypass that part. We can see that's starting to make sense. Looks like these footprints, these 3D files aren't actually correctly synchronized with their pads, but anyway, sometimes you get that. I suppose that's a bug in the library somewhere, maybe, or something. But yeah, so stuff like that, sort of habits of good design, things like that. You can do that kind of stuff. What have we got? So that's our input decoupling. Then we've got, oh yeah, that's our reverse protection diode, isn't it? So that goes between input and output. for sake of space, it would probably make more sense to use this as a vertical part. In fact, if we wanted to use this, so I might actually exchange that. So that's D6. So let's go back to CvPcb. Let's go to D6 for example. So we go back to diodes. So if we choose vertical one, let's exchange that for that. Resave this, and probably have to resave this as well. And then because we want to exchange that footprint, we go back to the netlist, we say exchange footprint, change, so it'll reread everything. Yeah, that should do what we want. So yeah, let's now change this. So this is now a vertical one, so we could have this sitting right here. For example, you know. Oh yeah, by the way, the keyboard shortcut to bring up the 3D view is Alt-3. Yeah, so I could put that on there, for example. We could have that just sitting right there. That would probably be fine. Then we want to have a look at these adjustment parts. So what's this? Adjust resistor. We got this resistor here, and this resistor here. Where does that connect to? That connects down there. That connects to ground. Okay, so probably makes sense to fit that. Maybe there, because that's going to ground. This is going to that pin. This one could connect possibly like that, and then that connects over here. Does it go anywhere else? It goes to here, so we could run this trace like that. Also got our anti-latch up diode. And again, this probably would be better off done as a vertical. So I might actually do that. But we'll see. What's this? D8. What's D8 anyway? Oh, I see. That's the anti damage diode because of this capacitor here. So that's in parallel with R4. So that could basically go right there, next to that. And that's in series basically with this capacitor. Where does that go? That kind of goes in parallel with that diode. So if we had this here, That should work. That's what is our output filter, I think. Yeah, that'll be C8. That's probably a bit small. We could add another bigger one in at some point. But yeah, what else? What else is there? Anything else connected to that? No, that's pretty much that. It's ground, that all goes here. This one goes there. Oh yes, C adjustment. That's where does that go? I think it goes between this pin. That's the annoying one. Because that looks like it's going to overlap no matter what I do. So our output. Because originally I wanted to run this output trace probably, you know, through here. In fact, we could have that coming down here and then drag this pad down to maybe down there. Hook that up there. Have that coming like that, which would make most sense. And then say we have this one come up there. That all sort of makes logic. And these will go off to ground, but it'd be nice if these 3D models actually made sense. But yeah, this capacitor here. Whoops, drag the actual thing. It's kind of annoying because that has to go from here to here. We could sort of well, let's see, this is a 2.5mm spacing. It's not particularly... Yeah, okay, well this capacitor... We could change this. C6, C adjust, C6, that's not... yeah, let's change that. Instead of a 2.5mm spacing, let's change it to a 5. So that gives us twice the space to work with. that like that. That'd probably work. That looks a bit better. Yeah, sometimes it's easier to do that way, and that is still fairly, that's actually probably more, that might actually be more like the size I would want for that part. So, you know, the 2.5 would probably make sense for the electrolytics, but if this was a ceramic or a film, then 5mm width would probably make more sense. So, yeah, we can have that coming out like that. That's probably logical. So that's the that half. So yeah, let's keep going. Let's do the other side. That's, you know, I don't know. That's fairly decent. It's not amazing, but it's fairly decent, I would say. We still have some space here where I can put, I mean, we can move this left a little bit, and we still got some space here. We can put a nice big output filter capacitor if we need it, which I may actually do. And I'll probably put this diode vertical. Yeah, it's a good idea actually. D10. So D10 and D9 would make more sense to do that like that. D9, D10, let's go to diode, vertical. Might have to change some other ones later as well. Yeah. Stick that there. And now let's have a look at the other side. So I've got these two regulators here. But the thing with this is, like I said, the pinout so for example, if this is a 337, we have all these diodes and resistors and capacitors here, and that'll make sense. But if this was a 79 series regulator, then this would be the ground pin, and this of course is our ground, our actual ground connections over here. So basically we'd omit this diode, we'd omit this resistor, we'd omit that capacitor, and this resistor here would be a just a wire link going from there to there, just to make that pin ground, and then all these other things would just be irrelevant. They just do nothing. So yeah, that's my idea for that anyway. Whether that's a good idea or not, I'm not sure. I mean, would this would these traces pick up noise? It's possible. Things you got to think of. But yeah, it's probably so close that it's not going to be a huge issue. But we'll see. Only way to find out will be to find out. So 7, 8. This one we don't need to have back from the edge of the board, but I mean, yeah, the flow of this, for example, is pretty obvious. You know, it's going to come in here. This just goes straight down to the ground, and this is our output. And then you have your capacitors here, and if that was just a 7, 8 series, then that's all you'd need, which is really, really simple. But if we're using the 317, then these pads are opposite. It's all kind of swapped around. So if I was to what's the best way of doing this? If I put that, now would it make sense to put that next to that one? Because I do want to be able to have the option of having the heatsink there. So maybe if we bring this about there, see, how would that go? That's our input. So we could route this behind it. That would work, I suppose. And this would connect to our output. So let's see, where's our output diode? That would be D9, won't it? Yeah, okay, D9. That would go about here. And then if we drag this pad, I guess we want this sort of equidistant from the ground, just like that one. I think that's about as far as it was, wasn't it? Oh, maybe a little bit. Yeah, that looks about right. We can check that actually with the measurement tool. So if we go to say comments thing, we can check the distance between this and this, which is 10 millimeters, and we can check the distance from this to this, which is coming up as 12. So yeah, we want to move this down 1, 2, I guess. Just delete that there and try that again. Yep, that says it's 10. So that's going to look a bit nicer than if we didn't have that like that. Not that it's a big deal. But anyway, that's just how I want to do it. So yeah, maybe if we have these two side by side, and then you just put whichever one in you want to use. Where's our output capacitor for that? C7? Okay, that's a bit small, isn't it? That's okay. Yeah, probably, like I said, I'll change these later, but probably be the most logical way to do it. And probably will have to have some wire link or something over here to just get this across from this pad to that pad. I think if I flipped one of these around and had it back to back, it would be alright, but then if you wanted to have a heatsink that was sticking off the side back of the board, it would wouldn't work. So it's probably best to do it this way. So yeah, what have we got? What's this pin? This is our adjust pin. Okay, so adjustment resistor we can bring, I suppose, like here. Maybe this one can just sit next to it. It's probably alright. Where does that go? Well, that just goes to ground, so that's fairly easy. Could just stick that by the side of that resistor. And this goes up to here, which I believe is the output pin. Yes, would have to be because that's the input. But yeah, that's well, where does that go? You've got that diode there. Oh no, actually. Okay, if we brought this, now I want to drag this over a bit. So we can highlight that and press tab and bring that over a little bit. Move that there. That works. I mean, we could save more space if we had these vertical, but this will do, I think. Now, we have still have some sort of input filter capacitor. It's going to go yeah, again, I think if we replace this That would probably make more sense if we stuck that in the middle there. If we bring that like that, but I think we want to replace that with a 5mm one as well, so that's C3. Oh wait, so C3 disk 5, yeah. Let's change that. Because we need to bring this down to ground somewhere. For example, let's just run a big trace right through the middle there. So it'll be our ground going through the middle. And this diode is, what is this? This is our reverse. Reverse output diode. Could we stick that over there somewhere? Maybe. Actually, that could work quite well. Makes sense. So that's our ground. Being that this is the yeah, so that's pretty much all makes sense, I guess. Except for the output for this one. So that's yeah, this has to connect. And we kind of can't get away with this really without having a wire link here, so I think we'll just have to have one. I don't think we can do it easily without one. So what I'll do is I can use a via for that. Make a pretend topside trace, which will just be a wire link. So let's see, if I click on here, let's go down to, I don't know, here for example, press V, you get a via that can go across, and then I press it again, we get that. So, you know, if this was a double-sided board, that would be a topside trace, but if this is a single-sided board, which it would be, you just insert a piece of wire in that space, and you don't print the top layer, obviously. So that's alright. I don't really like this decoupling capacitor, though. It's sort of, it's not close enough to that IC, and to be honest, it would probably make sense to have maybe actually have two of them. Yeah, possibly. One for this regulator and then one over this side. Maybe one down here from this output pin to ground. I'm not sure. What does this say again? Yeah, when they have an output capacitor. CA's output improves transient response, not needed for stability. Okay, so it's not really a huge deal. But utilizing that, you know, having that all the way over there, this is good for stability for this, for using a 7800 series, but if we had this over here, we'd probably want, I guess we would want like one maybe going from about here to ground. Yeah, just for, but that could be for the, yeah, okay, well, transient response. Oh no, we'll put a big electrolytic filter capacitor here, and have another one on this side as well for people that want that. And then that solves that problem. So then this will have its output thing, and then this already has its decoupling capacitor. That is its decoupling capacitor, isn't it? C8, I think. Was it? No. Yes, C8 is that one. It's the final output. It's the input decoupling sort of thing. It's the output. What does the 79 series say? Oh no, 2 is required for stability, so that's the input one. Prove transient response. Okay. So the output maybe is not necessarily necessary. Anyway, yeah. That looks like it's the critical one, which is already in a decent place there. Well, kind of. It's close to the input pin, but at the same time, it's the return current is going to have to travel all the way around here and back through that link to get to the ground pin if this was a 7900 series. So it would make more sense to locate this somewhere else, but it might not be a big deal, because what I'm going to do with all this basically is add a ground plane as well. So that's how we have this add filled zone. This is a good trick, not only for signal quality, but in some applications, but it's also a really good trick for when you're making your own circuit boards, because to speed up your etching time, you want to etch away as least copper as possible. So if you create everything with a large power plane or ground plane over most of the board, then that's all copper that you don't have to etch off. And if I go with this, right click on it, zone, fill zone. So for example, that means this is all going to be just a ground plane. If we have a look at this here, I mean this bit here obviously doesn't make any sense, but all this bit in the middle, it's quite logical to have all that done that way. So, you know, and then you don't have to etch all that off. You only have to etch these bits. And, you know, in this corner I might write something, put some text. Let's put dual PSU. Oh no, that's quite small. Let's see. Yes, so PSU. For example, we can have that there. So yeah, this 3D render doesn't look that great because these resistors are all not really matching up with their footprints. But, you know, it's ultimately fairly well done, fairly well makes sense. We've missed that out. And then we can refill the zone. Then we can probably delete this trace. It's a good idea here because, for example, these are sort of thermal relief things when you're soldering. You want to have that, otherwise it requires you to heat up all that mass with your soldering iron. So, to make things make sense, it makes more sense to delete these tracks here. Oh, I don't know, maybe that one could stay. And that one, to be honest. But the rest of it's not really necessary. So yeah, that's pretty much it, I guess. Again, like I said, this capacitor, I think I could probably put this in a better location. I might sort of move it. I might move these parts over a little bit and then fit this in here somewhere. But well, we could change where this resistor goes, actually. That would be the most logical thing to do, I think. If we turn this around so it goes in front of this, and we move this capacitor over here, and we move this diode. Maybe to there. I'm going to have to delete these tracks, redo them. Yeah, that's a much shorter return path. So the input side from this capacitor goes to this pin, and then return will go through this resistor if it was just the wire link. So yeah, that's a better solution, I think. But that's pretty much it. I would say there's not really much else to do. Like I said, I might put a couple of put some space for some bigger output capacitors in this corner maybe, and move all the rest of this over a little bit. But I would say that the majority of it is pretty much done. We've got a fairly decently laid out board, I think, by my own standards anyway, which should be perfectly serviceable for what I need. It fits within the size that I needed, and everything basically just looks fine. So yeah, that's pretty much it. This video will be pretty long now, I think, so I'm going to stop it here, I guess. But aside from that, though, you can sort of export your different files. So for example, for me, I'm going to want to export this as What is SVG? I don't think I've ever used that. But you can say plot the thing to PostScript. That's what I usually use. So we want to plot that. The edge. And we want to choose drill marks. We want actual size. That gives us a sort of pilot hole. Plot mode, filled, scaling. That looks good. So if we plot that. Now there used to be an option you could oh, there we go. I think we want that. So it'll put this edge on the thing here, but if I open this now, if I open up Inkscape, I should yeah, so there we go. We've got our basic artwork there, so I can just print that out. You can also print directly from KiCad, but you can either go here, file, print, and all this stuff, but obviously that's going to print it in the center of the page, which is a A4 I think by default. Yeah, so that's going to be, so your A4 page is about this big, and that's going to be in the middle. If you export it first, then you can edit it, and you can say I want like 3 copies of it. I can just copy this and put another one in, and have a bunch of them, and then I can print, or how heck I could print, I can put 9 on a page or something if I wanted to, and more efficiently use the and then I've got I can efficiently use the whole transfer sheet if I wanted to make, say, 9 copies of the same board, which is much easier than printing it from here. This is good to print for a test, for example, if you want to just print a paper copy of the board, and then you can check the location of things, check the sizing, all that kind of stuff. But yeah, it's much easier, I think, if you do it this way. You can then mess around with it, add other designs at the same time, print them all at once, that kind of stuff. So yeah, that's basically it. Yeah, I just realised I'm going to have to put some mounting holes actually as well, so that can go in these corners, and I'll have to move these diodes a little bit, I guess. Maybe I might make these ones vertical or something, so I can get the holes in the corners there, or possibly put a hole there. But yeah, that'll just be some minor sort of tweaking. I probably won't bother showing that. Like I said, this has already gone long enough, and this does show the overall pretty much general thing. I suppose the only thing I would change maybe is I'll show you how to edit the pad. So for example, I want to edit this pad. This has got a small hole. This hole's probably too big, so let's go pad here. Pad 2, edit pad. Drill size, it doesn't have to be, where is this? Drill, they've moved that over here. Okay, so 1.2, it's not going to need to be that big. We can make it say 1mm. Just like the other one, that makes more sense for a diode. Like that, it's going to be about that. And we notice that all these other diodes here have the same problem. This hole is bigger than this one, so I can go here, pad 2, edit all pads, and if I want to change this, so we choose change pads on identical footprints, and that'll automatically update these so that all these diodes have the smaller hole there. So we do the same with these as well, but that's basically it. That's kind of one of the most common things I find myself having to do, is to change the drill hole sizes on some parts. But yeah, that's pretty much it. I wish the 3D models were all correct and they looked sensible, but that's it as it is. But that's basically that's obviously I've probably not used the best design practices here, the best layout sort of things, especially with regard to this bit here might be a bit silly, but it should work probably for what I want. So yeah, don't assume that everything I've done is perfect. If you do want to lay out a board properly, you have to look at all the signal integrity requirements and all that kind of stuff and make sure everything makes sense. But for the basic thing of just how to basically do something like this, it's this is, I think, the most obvious way of doing it. It's just important, I guess, is to make sure your traces are actually nice and thick for what you're using, especially if it's a power supply or something. And if you are, not to just run stuff around the board, have things as direct as possible. And if you have decoupling capacitors and that, you want to have them so they're actually in line with the actual trace and not sort of sticking off on the side. So for example, like this one here, the input comes in here and it goes straight to this one terminal of the capacitor, and then it feeds out to both the regulators, which makes more sense than if we had this coming to this regulator and then to this one, and then we had a decoupling capacitor somewhere else. Then it's sort of the current goes first to this, it doesn't go to the actual component you want. So if you have this directly in line, then it kind of has to go through there, and that just helps cut down on noise and things like that, I think. So, but all that kind of stuff is a big topic into itself, and I'm not an expert, so I'm not going to try and explain all that here. But this is just something I just wanted to show, just a basic sort of thing. So anyway, I hope you enjoyed that, and hopefully it's informative in some way. And I guess that's pretty much it for this one. But wait, there's more, as if this video wasn't long enough already and hasn't already probably put you to sleep. So while I was editing the previous segments that I'd already recorded and waiting for the thing to render the screen capture, because it doesn't render it in real time, my computer's not fast enough for that, I worked on the board some more, and I've got what I think is probably the 99% or complete version, final version. I did change a few things. Like I said, I added these space for larger output capacitors. You don't need an output decoupling capacitor on these regulators. You just need some decent filter capacitors if you want good transient. If the circuit you're running is going to draw some quick spikes of current, then it's a good idea to have some decent output capacitors on the power supply, so that the regulator can keep the voltage up well enough, so that it doesn't, the regulator itself probably won't become unstable and start oscillating or anything, but you may get voltage fluctuations which could affect the load. So you want these output capacitors for just general voltage stability, basically. The regulator itself, though, really only needs the input decoupling capacitor, which I've got on both of them. And again, that's only really necessary, it says in the data sheet, if the regulator input pin is more than like 3 inches or something away from the main filter capacitor. So you'd probably only actually need to add these capacitors if you weren't using these filter caps and you weren't using the rectifier diodes, and you already had a rectified supply that you were running wires from, and then it was a longer distance away, and then you may need these. But in general, you could probably get away with just having these and just having these. Saying that, though, I probably wouldn't recommend it. I think I will be putting these capacitors in anyway, just in case, I guess, but for this sort of thing it may not be necessary. The adjustment decoupling capacitor is probably a good idea, especially for the since the adjustable regulators, the 317, 337, they are claimed to be lower noise than the fixed series. So specifically for me, using this primarily for an audio preamp, I would want the lowest noise possible. So to add those filter capacitors to the adjustment pin apparently provides the best stability and lowest noise for that sort of thing. So that's definitely what I'll be doing there. I guess if you didn't care about that and didn't mind a higher noise, then you could use, you probably wouldn't need that. You just need the resistors to set the desired voltage. But yeah, yes, and I decided to replace those fixed resistors with a couple of 10-turn trim pots because I figured that having space for those just makes more sense. Yeah, so you could mount horizontal ones like shown here, or you could have vertical ones, doesn't matter. I made it so the horizontal ones would sort of face opposite sides of the board so you could get a screwdriver in there. There's things like that you've got to think about when you're designing it to make sure things actually make sense. That's why a good idea why you should do a print copy first just on plain paper and actually physically sort of put the components on the paper where they're going to go and just check that. And that's also a really good idea, especially if you've created a custom footprint for maybe a connector that you haven't used before or something that isn't in the library. You have to make your own footprint for that, and or just checking the fit clearance and things of stuff. So I'll be doing a test print of this definitely before I actually go to etch it. But yeah, so that's pretty much done. 10-turn trim pot is a good idea for these adjustable regulators if you want good precision. I mean, you can just calculate the basic value and then just put a fixed resistor in, but obviously the fixed resistor will have a tolerance that may be, it depends on how much precision you want. In most cases, 1%, 2% resistor should be perfectly fine for most people, but if you really want to trim it down to a really fine value, then having a trim pot there is good. And obviously you could put a fixed resistor in there anyway if you wanted to. Doesn't matter. So that, or if you're using one of these 7900 or 7800, you just put a wire link there and omit this capacitor and omit this resistor here. So the trim pot gets replaced by a wire link, and these capacitor and resistor out here, they're not there. Everything else would obviously stay the same. The reverse, this diode is not necessary if you're not using this capacitor. The adjustment decoupling capacitor, if you're not using that, you don't need this diode, but the reverse protection diode is probably a good idea. Again, you don't necessarily need that depending on what you're doing, but I don't know, it's worth putting it there, I guess, just in case. It's cheaper than a new regulator. Yeah. Also, obviously, I made these mounting holes here in the corners, so that's where I'll be able to drill. I had to move these diodes over and sort of cram these ones in here and just sort of push the pads in a little bit closer, which will just mean I'll have to bend the leads a bit tighter, but that's fine, that should fit. Although, of course, if you did get them too close, it wouldn't fit, so that's another reason why you should print out stuff on paper and just do a check first, just to be really sure that things actually are going to work. But yeah, and this cutout here is just because I'm using an old scrap sort of piece of blank copper board, so it's already had a hole drilled in it in this position. So I've just put that there to remind myself that I can't place any tracks in that area because there's a hole there. Obviously for most people, you're going to be using unmolested board that doesn't have holes randomly drilled in it already, so it won't be a problem, but yeah, just that's why that's there. But I'd say, yeah, this is pretty much done now. I'm just going to do a test print and check these diodes just to make sure they actually fit. Of course, if they didn't fit lengthwise, I could always just mount them vertically like these ones are already going to be anyway, so it doesn't really matter, but that's the kind of thing you want to just have a look for. I did move this link to the other side of this diode because I figured it had a shorter path and it'd be better. And I added some, I filled in this track in like its own little, I didn't give it a zone but I just sort of filled it in with overlaid tracks. Same with this part here to make a little sort of land and for these things. So that kind of makes things neater and again saves copper and makes the etchant go faster. But yeah, just little tricks like that are always good to do rather than you know, having just really thin wires running around. You keep things thick and nice if you can. But yeah, that is pretty much it for the design of this. I don't think I'm going to change anything unless there's just like a component that doesn't fit and I have to move it around slightly. But I'd say the layout of this is probably what I'll be using. Okay, so there we go. Assuming you haven't fallen asleep by now, you can see that I've got the final design, or pretty much I'd say final design, and I'm ready to print it out and etch it soon. So watch out for the next video where I'll be testing out the Chinese yellow transfer paper on this piece of board and actually doing this transfer and just seeing how it comes out. But yeah, I mean, you can make this this thing in a couple of hours. Obviously, it's a simple board, doesn't take a huge amount of time. Probably could be done faster, but hey, it'd be nice if there wasn't a chainsaw in the background. So there we go. If the previous 2.5 hours of that video put you to sleep, the chainsaw in the background will now wake you up. Well, saying that, you probably can't hear it at all because the background noise cancelling, but whatever. Yeah, so I mean, there we go. Simple board, only takes a little bit of time. Obviously, a more detailed one would take longer. I didn't show everything in KiCad. There's a lot more features that I didn't show. If you want to learn about that, then you know, download it, have a play, have a look at some other videos and that. But this is just the basic thing of how to get a basic thing working. It does have the push and shove routing in that nowadays in this new version, which I didn't show in that either. But I mean, you don't really need to for something this simple, really. There's no point. But it does have it, which is quite useful. They just recently added that. Yeah, anyway, so all I got to do now is just print this out, do a test fit, make sure it actually fits on the piece of board that I'm going to use. I mean, it should because I measured this and did everything properly, but, you know, just to be sure. And check that the components fit. This is the old bit of board. This is the new board it'll be going on to. Yeah, I probably won't be using these regulators. I don't know if there's something wrong with them, or, well, there shouldn't be, but, you know, I'll probably use the 317 and the 337 anyway, because, like I said, they are lower noise, apparently, so that would make sense for audio stuff. But yeah, there we go. So that's it. That's how you design a circuit board in a schematic, put a schematic together and design a board layout from it in KiCad. It's not really, like, very complicated, it's just you have to know. Like, I mean, using the program is not complicated. It's really, it's just, you know, you have to know what the design is, and you have to know how to do that. Basically, that's the hard part. Is not the not actually using the program, in my opinion. It's just the actually knowing what to put where and whether your design's actually going to work. So, yeah, that's the fun part of electronics, is actually getting the design to function. So yeah, I'll put the files for this up with a link once I've actually made it and tested it and make sure it actually works. I'm sure it will, but you know, just in case. So they expect that to be a couple of days or something. But I should do this next video soon when I actually do the transfer for this and see how it goes. But there we go. That's that one there. So hopefully you enjoyed that one. Hopefully you enjoyed how long it was. I'm going to guess it's about 3 hours now. Longest one I've made yet, but hey, why not? I just felt like doing the whole thing, so yeah. Anyway, hopefully it was enjoyable. Hopefully you got something out of it, even if all it did was send you to sleep. Yeah, anyway. Yeah, so I'll see you next time.